The next presenter is Sam. Sam, are you here? You said yes. Okay. Yes, Sam Teitelbaum from Arizona State University. We have a lot of people from Arizona, and Sam is opening this batch. Thank you.
Yeah, thank you, Michael. Thank you for the invitation and for organizing this talk. It's great to see everyone. So today I want to talk to you about some work that's been going on for, I'd say, the past 7 years, from when I was a graduate student in Keith Nelson's group at MIT to my postdoc in David Reese's group in SLAC and continuing on in Arizona State University. And the themes that I'm going to talk about here are things that you'll probably hear more about in this conference: metastable phases, and this idea that what we really want is to be able to do condensed matter physics by approaching a problem with multiple probes. And I want to start this off by understanding first what I mean by metastable phases, and also some ideas that we have for how they're formed and stabilized. Everyone can see this presentation view, right? Yeah, fine.
Yes, you're good.
Okay, great. So here is what we currently understand a little bit about what the important sort of ingredients are for forming a light-induced metastable state. And by this, I mean something like what Keith just gave a nice presentation on last on the TMDs, which is something where we induce an ultra-short light pulse and the response is persistent. So it lasts for hours or days or until we apply some sort of reversibility, right? Heating the material up. There are many examples of this. Tantalum disulfide is a famous one. The one I'm going to talk about today is the manganites. And what these systems seem to have in common is first, complex equilibrium phase diagrams, right? So there seems to be this need to have some kind of competing order in the system. In other words, different kinds of order, whether these be different kinds of charge density wave orders, or in this case, charge order and ferromagnetism, or in the vortex supercrystal phase that's been led by Vladimir Stoica, the different kinds of ferroelectric ordering. And the vortex supercrystal phase is also a good example of the idea that one of the other key ingredients here is the formation of defects and traps and slow relaxation. So typically in ultrafast science, we think of collective excitations. We think of things like A1G modes, where the entire system is doing the same thing at the same time. But that's not necessarily true at long times. And we've seen that in systems from tantalum disulfide to the manganites, that things like domain walls are really important for stabilizing these new phases. And finally, we need strongly coupled degrees of freedom. And this feeds back into the complex equilibrium phase diagrams. So in the manganites, what you have is strongly coupled lattice, charge, and magnetic order, which I'm going to talk a lot about in some detail today. And in other systems, you can have, for example, strongly coupled lattice and charge order in the TMDs. And this is important because, again, you need this activation barrier between your sort of hidden metastable photoinduced state and the ground state. And that's what the strong coupling gives you. So experimentally, how do we tackle these kinds of problems? Well, in order to build a comprehensive picture of competing order, ideally, we would like to be able to probe all of these orders simultaneously in the time domain as they evolve. So in this talk, I'm going to talk about 3 kinds of probes: optical spectroscopy, X-ray scattering, and terahertz spectroscopy, which are going to probe our charge and orbital order, right? The alternating manganese oxidation states in particular. The lattice structure, in particular, we're sensitive to a monoclinic to orthorhombic transition. And terahertz spectroscopy is going to be able to probe charge localization. And charge localization in the manganites is intrinsically related to ferromagnetism. So you can think of the terahertz response as probing how far along you are towards the ferromagnetic state. You can think of the optical response as what does the local electronic structure look like. And you can think of the X-ray scattering as probing what the long-range lattice structure and what the long-range charge ordering looks like. So before I get into the details of the ultrafast spectroscopy and what photoexcitation is doing to this system, I want to take a few minutes to talk about correlated electron materials and transition metal oxides. Specifically, what makes these systems, what is the underlying physics behind the competing order in these systems, and why does photoexcitation manipulate this order? So one thing to understand is that manganite physics is dominated by d orbital interactions. So every manganese atom in the system is either generally a manganese 3 or a manganese 4 oxidation state. And in these slides, I've shown you the d orbital manifold drawn here in the cubic configuration, where you have an Eg orbital and you have a T2G manifold. And because of Hund's rules, you end up getting 1 electron on each of these orbitals. And this is at several eV energy, so it's much larger than the temperature, this exchange interaction. On the other hand, the tunneling interaction, essentially the hopping interaction between these 2 orbitals, is on the same order as the Jahn-Teller distortion. So because you have, in this case, you have equally occupied orbitals, so you don't get a Jahn-Teller distortion. But if you have another Eg orbital, which I haven't drawn here, which is unequally occupied, that gives you this Jahn-Teller distortion. And the Jahn-Teller distortion is on the same order of energy as this hopping interaction. But even more importantly, this hopping interaction is controlled by the angle between the 2 perovskite octahedra. And what that means is that by controlling this octahedral rotation angle, you control the intersite coupling. And so this can tune between a ferromagnetic state, which likes a lot of intersite coupling so that you can get good conductivity. Essentially, it favors hopping interactions. On the other hand, if you have, let's say, a lot of d orbitals everywhere, you would not favor hopping interactions because you want this manganese site to be all spin up and this manganese site to be all spin down so that you can hybridize this d orbital with this d orbital through the p orbital. This is known as the super exchange interaction. On the other hand, if you have an empty d orbital, then you would like all the spins to align to favor Hund's rules. And so if you have a system with manganese 3 and manganese 4 ions, you can have both anti-ferromagnetic and ferromagnetic favoring interactions in the same system. And the way that you balance between the two normally is you would change the doping, or you would change the manganese oxygen manganese bond angle. Or you would change the temperature. And so depending on what temperature, hole doping, and bond angle you have, you can end up with all sorts of different states. You can end up with charge ordered insulators, which is what we're going to start with in this talk. You can end up with ferromagnetic metals, which is what we're going to end with after photoexcitation. You can end up with paramagnetic insulators, which is essentially the disordered sibling of the charge ordered phase. And you can end up with mixed order phases. So you can end up with phases where, to balance out the competing strain, you end up with some volume fraction of a ferromagnetic state and some volume fraction of an insulating state. And so I should mention that, at least at equilibrium, a lot of these phase transitions are first order. There's a change in the volume of the unit cell, and you end up with phase segregation being a very important aspect of the equilibrium physics in these systems. So since we know that the strain and the unit cell volume is very important to controlling the phase, we're going to use that in the first part of the talk. So what I'm going to talk about today is essentially trying to go from a ferromagnetic metal into the charge ordered insulator phase at constant hole doping by changing this manganese oxygen manganese bond angle by applying a strain. And so the system we're going to study today is an epitaxial thin film of LCML. So this is 1/3 doped LCML. In bulk, it's a ferromagnetic metal. However, when you deposit it on a thin film that has a different lattice constant, the epitaxial strain that you get from the thin film is going to change that manganese oxygen manganese bond angle, which is going to change the hopping interaction, which is going to favor the insulating state. And so what we've done here, and this is where the ultrafast science starts to come in, is that we've tuned this material to exactly very close to the boundary of the phase diagram between these insulating and magnetic phases. And so when we cool the system, this is now terahertz spectroscopy. So I'm showing the conductivity as a function of temperature using terahertz transmission spectrometer. And when we cool this material, we see that the conductivity goes down with temperature, right? This is an insulator, and as you cool down, any sort of residual conductivity that you're getting from thermally activated conductivity is going away. However, at 80 Kelvin, if you apply a short laser pulse, the conductivity suddenly jumps to about 1,000 to 1,200 inverse ohm centimeter. And this black curve up here, I should show you, this black curve is the conductivity of the pristine, unstrained metallic phase. So this is the conductivity of essentially bulk LCMO. And so the conductivity jumps up almost to the bulk level. Then, if you heat the material, the conductivity goes back down to its insulating state around 120K. And by 140K, the material has, at least in terms of electrical conductivity, returned to the insulating state. So what we can do is essentially, photoexcitation is taking us permanently from the insulating state to a metallic state. And then heat is annealing away this photoinduced metallic state and taking us back to the insulating state. And if you look at the sample under a microscope, if you just look at the optical reflectivity over here, so this 100 microns is about the size of our laser spot. And you can see this dark spot after one laser shot showing up. And after 2, 3, and 4 laser shots, this dark spot gets a little bit darker. And so what you're seeing is that not only do you have the change in the electrical conductivity measured by terahertz spectroscopy, but you also have a change in the optical reflectivity. So why is this happening? Why do you see the change in the optical reflectivity? Well, the two phases have very different optical properties. So on the left here, I've shown the ferromagnetic metal, and this is the imaginary part of the conductivity of the dielectric constant. So this is the absorptive part. And here's the charge-ordered insulator. The charge-ordered insulator has a peak in the conductivity around 1 eV, and the ferromagnetic metal has this large Drude peak that goes to large values at 0 frequency. And in the charge-ordered insulating phase, this peak also redshifts and disappears at higher temperature. So this peak here is indicative of charge ordering. And what it is intersite charge transfer. So this is an excitation which takes a manganese 4, an electron from a manganese 3 ion and transfers it to an empty manganese 4 site. So at this point, it's good to mention that this insulating state is what's called a charge and orbitally ordered state, which essentially means that the oxidation state of every manganese alternates in the unit cell. And for the manganese 4s, they have a Jahn-Teller distortion and they have a particular EG orbital polarization. And this EG orbital polarization also alternates. So you get this sort of double checkerboard pattern where you have imagine a checkerboard where all of your black squares are manganese 4s, all your white squares are manganese 3, and then every other manganese 3 has an alternating orbital polarization. And what we're doing with photoexcitation, so this tells us two things. One, what we're doing with photoexcitation is we're exciting a whole bunch of these charge transfer transitions, and we're essentially scrambling the charge order in the system. And this is what allows the ferromagnetism to emerge. The second thing is that means that the reflectivity in this region, in the visible, is going to be our probe for how much charge order is in the system. And this is what you can see here. So on the left, I've plotted experimental data. This is just reflectivity from a visible spectrometer taken as a function of the incoming laser fluence. So each of these reflectivity plots is the change in reflectivity as a function of fluence above the switching threshold. And on the right, what I'm plotting is the predicted change in reflectivity. And the experimental plot is this tail here. The predicted change in reflectivity as a function of essentially the switched fraction. So all I'm doing here is I'm modeling the reflectivity of a thin film of LCMO on our substrate with some fraction having a dielectric function that looks like the insulating LCMO and some fraction that has a dielectric function which looks like the metallic LCMO. And what you can see is that these quantitatively reproduce our experimental results. And they agree with the terahertz spectroscopy. So if the terahertz spectroscopy tells you that about half your material is in the insulating phase and half is in the conducting phase, qualitatively and somewhat quantitatively, and I'll get to that later, the optical reflectivity data agrees with this. So now, what is happening upon photoexcitation? What's happening in those first few picoseconds? So if we do conventional pump probe spectroscopy, then we can see, at least below the switching threshold, what the material is doing to respond to this photoexcitation. And here are some pump probe traces taken as a function of fluence at 80 Kelvin on an LCMO NGO film. And these are all below the photo switching threshold for this film. So this can all be done stroboscopically. And what you see is some very strong coherent oscillations here. These are this 2.7 terahertz mode, and some smaller oscillations, which you can make out just at the beginning here. And if you do your background subtraction and your Fourier transform, you'll see that there are actually 4 distinct modes in this spectrum. And what these 4 modes are, this 2.7 terahertz mode is what's known as a cation mode. We'll get back to it later. It's essentially the lanthanum and calcium ions moving around to accommodate the oxygen octahedral rotations. And these 6.9 and 10.3 terahertz modes, these are octahedral rotations. So these are the modes that are taking your manganese oxygen bond angle and changing it. So not only does the manganese oxygen bond angle favor or disfavor charge ordering, but destroying the charge ordering will impulsively change that bond angle. And finally, this 15.6 terahertz mode, this broad mode here, is a Jahn-Teller mode. So this is basically a coherent oscillation of the Jahn-Teller distortion in the manganites. And this is all consistent with literature. So we're not the first people to publish this. Andrea Cavallari and Simon Wall and many others have seen these coherent phonons in manganites. So now we need to understand what's going on in the first few picoseconds of the photo switching phase. And for this, we turn to single shot spectroscopy. So with conventional pump probe, we're unable to see what's going on within the photo switching because once the material is photo switched, it's permanently in the magnetic phase and you need to wait to warm it up to take it back to the insulating phase. You can't do that with a second ultra short laser pulse. You'll just end up making more metallic phase until the system saturates. So what we use is single shot spectroscopy. And here I'll just briefly mention this. So what you have here is a single ultra short laser pulse represented by this flat square. And then it's passed through a pair of these echelons, which are essentially glass staircases. And what the glass staircases do is the part of the beam that goes through more glass arrives later. The part of the beam that goes through less glass arrives earlier. And by having a pair of them, we can make essentially a 2-dimensional grid of little beamlets that are a 2D array of time delays. By focusing these beamlets onto our sample and imaging them onto a detector, we're able to measure something about the sample. Michael, how much time do I have? Sorry, you're muted. Okay.
5 more minutes. 5 more minutes.
I'll go much faster.
Questions, yes. 5 more minutes
Okay.
for questions.
Okay, so when you do these single shot measurements, essentially what you can see is if you image your echelons onto the detector and then take the average of each of them, then you can extract a single shot trace. And what we find is that the reflectivity drop, so this is the reflectivity drop as a function of time in picoseconds. And what we can find is we can connect now the amount the reflectivity changes with the switching threshold. And what you'll find is that the dynamic reflectivity drop saturates, as does the final photo switching threshold. And the reason the static reflectivity saturates is because you can't melt more than 100% of the charge. And what we can do is we can connect this switching threshold at 2.2 millijoule per square centimeter to the total amount of charge order melting. So essentially at 8 millijoule per square centimeter, you're melting 100% of your charge order, which is this reflectivity change here. And when at the switching threshold, you're melting about 1/2 to 3/4 of the charge order. And this will become important later. So in order to understand and quantify this more deeply, so now we know that we're melting the charge order, and that if we melt about 1/2 to 3/4 of the charge order, we can begin to photo switch. So we took this sample to Argonne National Lab and cooled it down and did these experiments now with an X-ray probe. And what you can see is that there's a structural phase transition on top of, again, with the unit cell doubling that's associated with the charge ordering. So this blue box shows you the unit cell of LCMO at room temperature. And if you cool it through 255 K, you'll see a doubling of the unit cell, and this new peak, this monoclinic peak, appears with increasing temperature. And then if you photoexcite the system, this monoclinic peak starts to disappear. And so you can think of the metallic phase as essentially a partial recovery of the high symmetry state. Then we took this sample to LCLS, and at LCLS, you can pump the same monoclinic peak. And what you'll see is that the monoclinic peak is suppressed, and as I'll show later, it doesn't recover for a long time. But we can model that suppression of the monoclinic order, because now a drop to 0 perfectly corresponds to a complete melting of the charge order. So here's our experiment. And what you can see is that at about a 50% drop in the intensity, which is about a 75% drop in the charge order, which is represented by this model of eta as 3/4. This is approximately the photo switching threshold, which we can again measure because we know at what fluence at LCLS we start to see a loss in the monoclinic peak. And again, this is very reminiscent of earlier experiments by Paul Bode and Urs Stubb and Steve Johnson's group on the manganites, where they also observed this coherent oscillation of the cation peak along with a loss in the structural superlattice. And our model, by the way, our theoretical models are based on the same idea as theirs. So what we did to model this was used a extension of Ginzburg-Landau theory. So in traditional Ginzburg-Landau, you represent your free energy as a even order Taylor expansion in the order parameter. Here we have 2 order parameters. We have a magnetic order represented by M and a lattice order parameter, essentially the monoclinic phase represented by L. And then we have this coupling term. And this coupling term essentially tells you that you can't have ferromagnetic and antiferromagnetic order at the same time. They compete with each other. And if you draw a potential energy surface for this, or a free energy surface for this, you get something that looks like this. It looks like a double well. And the idea is that this deeper well is the true ground state of the system, the charge ordered phase. And the shallow well is the metastable state. And so what's happening is photoexcitation is taking you from the charge ordered insulating state to some highly excited state where charge order is not stable. And then the system relaxes into the ferromagnetic state. By the time the charge order gets a chance to recover, the ferromagnetic order is already formed, and the charge order can't recover out of this potential barrier. And because you have this model where you can essentially tune the charge ordering temperature with photoexcitation, you can ask, okay, at what photoexcitation level, eta, do I see a disappearance in this activation barrier? At what level do I see a disappearance in this activation barrier where at a highly excited level, I would enter the metallic state? And if you plot this barrier height as a function of excitation level, you'll see the barrier is around eta as 0.75, which agrees quantitatively with our experiments. Okay, I'll just wrap up. I just want to say quickly that this isn't the end of the story, because we also did single shot terahertz spectroscopy. And what you can see from this is that it takes a very long time for the macroscopic metallic conductivity to appear. It takes more than a nanosecond. And so this isn't a coherent approach to the metallic phase, but rather it's a coherent loss of charge order followed by a long evolution into the metallic phase, because the charge order can be suppressed for a long time. So with that, I just want to leave that for questions. I just want to conclude by saying that this was this wouldn't have been possible without many collaborators at LCLS, at Argonne National Lab. So the experiments at Argonne were performed by Vladimir Stoica, myself, some folks from David Rees's group, Jingdi Zhang, who initially discovered this photoinduced state. The samples were synthesized by Wenbin Wu's group at USTC, and the single shot measurements were performed in the group of Keith Nelson. And the coherent phonon spectroscopy was performed in the groups of Keith Nelson and Rick Everett.
Yes, we have a question. Jim, please.
Hi, Sam. That was a really neat talk. Does percolation play any role in this? I mean, you're creating these sort of metallic islands, and then somehow to get the conductivity, it has to connect through the whole system. Is that the source of this really long nanosecond?
That's a great question. And the answer is, we believe that percolation in the traditional sense doesn't play a role. And I didn't get a chance to talk about this, but the reason is because if there were percolation and phase segregation, like you mentioned, you should see an enormous broadening of the monoclinic peaks, right? You should see domains and diffuse scattering around the monoclinic peaks when you do the pump probe experiments, and that's not observed. The second point I'd want to make is with terahertz spectroscopy, you're really measuring the near DC dielectric response function. And when you think about the mean free path of a electron at terahertz frequencies, your domains could still be quite small, and you wouldn't necessarily see, you don't necessarily need macroscopic conductivity the way that you need for a 4-point measurement, where you do need essentially a metallic path from point A to point B. But no, it is a good question. And I should point out that I think the interesting follow-up is that I did all of this modeling with the Ginzburg-Landau model, but that is appropriate for a second order phase transition, and manganites are known to be quite first order. So the question, I think, is there a real change in the unit cell volume, which is something that's not usually assumed at very early times.
Thank you. Matthias, please.
Okay, super quickly. Can you estimate how much energy goes into the phonon system and into the phase transition when you photoexcite the system? Do you have, I don't know, an idea about the energy that goes into the specific heat of these two systems?
Yeah. So when you photoexcite at about 2 millijoule per square centimeter, if you were to thermalize everything, you'd get maybe 30 or 40 K temperature jump. It's not a lot. You're getting a lot of energy into the electronic degrees of freedom. You're essentially, if you want to think about where the entropy is going into destroying the orbital order. And that takes a long time to come back.
And that's the major fraction of the energy. So you pump more into the disordering than into the phonon disordering, yeah?
Yeah, so this is the idea behind, this is actually important for the this time-dependent Ginzburg-Landau theory. So if you ask the question, why can you think of, if I maybe go to this picture here, why can I think about this as coherent motion on a potential energy surface, right? This is a Landau theory, it should be a free energy surface. And the answer is that if all the entropy is going into the electronic system, then the phonons essentially see something that looks like a potential.
Mm-hmm.
And that's why I can build this model this way.
Sasha, please.
Yes, thank you. Well, very nice talk, and I have a very brief question. So how long does it take for this ferromagnetic state to relax, basically for material to go back from this ferromagnetic state?
Oh, you mean how long does
it persist? Yeah.
Oh, how long does it persist? It depends on the temperature. So I can't give you a good answer. Because you're asking essentially, if I were to heat the material quickly to 140 K, how long would it take for the conductivity to drop? We can't heat it slowly enough in order to not see something that we think is mostly just the cryostats ramping rate. On the other hand, if you try to heat it too quick, if we try to heat it by thermalizing with a laser pulse, that is not quite the same mechanism because our lasers are resonant to a charge order transition. So I don't think that it would be appropriate to think about the laser as heating even at very long times.
Okay.
So I don't have a good answer for you. If you're asking how long it lives at 80 Kelvin, the answer is we've kept it in the ferromagnetic state until our cryostat ran out of liquid nitrogen.